And I built a handout for it, and all of the original source files are inside your download packet. I got a lot of models here, as well as the end of this has a couple questions where you could modify the model to answer the questions, and the answer keys are in here. So this involves yesterday's data, where we were predicting risky behavior. Remember that? And we found that the best fitting model was a fixed quadratic random linear. So the individual trajectories for risky behavior across ages 12 to 18 are right here. It looks like risky behavior is increasing over time, and it's doing so in somewhat an accelerated fashion. So I had set the intercept at age 18 because that was where most of the variability would be. Your activity from yesterday was to figure out what the optimal model would be for change over time with respect to monitoring. And the trajectories for this are right here. And I'll give you the spoiler alert. This is an instance in which there is no significant fixed effective time, but there's a random effect. So if I were to draw a line through this in terms of the means, it would be pretty much flat. But that's because some people are having their parents decrease their monitoring over time, whereas others are having to increase their monitoring over time. So these data are simulated, but they're based on real data that I had a chance to play with when I was at Penn State. So the question would be, is it the case that having more parental monitoring is a good thing, like it helps prevent someone's risky behavior? Or is it the case that girls who are engaging in more risky behavior need to be monitored more closely? Like there's sort of a yin and a yang relationship here. And in fact, if you look at the spaghetti plot combination of monitoring over time on the x-axis in risky behavior, there's a negative relationship through that. So when there's more monitoring, there is less risky behavior within persons. So this is an example of what I would call a multivariate model, because we're going to be modeling individual differences in intercepts and slopes in risky behavior and in monitoring, and examining how those intercepts and slopes relate to each other, as well as within persons, how risky behavior at a given occasion relates to monitoring at that same occasion. So the idea is deviations from the trajectory. If I have this trajectory and I'm higher than predicted at a given occasion on monitoring, does that mean that I'm higher or lower than predicted on risky behavior? So I built these data to have three distinct ways in which monitoring and risky behavior relate to each other. And I wanted to show you how to then recover those particular kinds of relationships. So the model that I'm going to start with is right here. This is a way of writing a multi-level model for univariate software. And this model could be estimated in Elmer or any other univariate software package that allows you to have correlations among the random intercepts and slopes, as well as correlations among the residuals. So we have a level 1 model that pertains to terms for risky behavior, which is quadratic, a level 1 model that pertains to terms for monitoring, which is linear only, and I'm having attitudes predict both the intercepts and slopes for monitoring and risky behavior, and having only a fixed quadratic for age. So the first model that I want to show you is just letting the intercepts and slopes be correlated, and letting the within-person residuals at the same occasion be correlated as well. Yes, we are recording. Good deal. So here is some Mplus code. I did not do the same model in Lavon because Lavon doesn't allow t-scores so that we can have exact change. So this is an example using stacked data, where we're building on the code that we looked at yesterday so that we can predict risky behavior and monitoring at the same time. So in terms of the stacked data set, attitudes is a time invariant predictor. That's only a between variable. Time and time squared, so that's age minus 18 and age minus 18 squared, are only within variables. Monitoring and risky behavior are going to be at both levels. So here's my within model, where I've got the level 1 residual variances for each variable. Then I have 3 different placeholders that define linear and quadratic age slopes for risky behavior, as well as a linear age slope for monitoring. And then I have a residual covariance that allows the occasion-specific residuals at the same occasions to be related to each other. Then in the between model, here are my fixed effects. So I've put everything in brackets. When you mention the variable, you're talking about its fixed intercept. And the rest of these fixed effects are defined with the placeholders in the level 1. So these are my fixed linear slopes and fixed quadratic slopes. Here are my random intercept variances, my random slope variances, and I shut off the quadratic slope variance because we didn't need that. Then we have our effects of time invariant attitudes, and then all of the relationships between the intercepts and slopes for monitoring and risky behavior are phrased as widths, which means they're covariances. Last but not least, because I wanted to get correlations, and those are not provided directly, I made them myself. So I used model constraint here to create correlations among the residuals, among the intercepts, among the slopes, and then the cross combinations of intercepts and slopes across variables by taking the covariance and then dividing it by the standard deviations of each of the variables multiplied together. So just the standard way of converting covariances into correlations. So this is the idea of two growth curves operating simultaneously. Everything's correlated with each other, and then the occasion-specific residuals are also correlated across the two outcomes as well. Okay, with me so far?
Are there missings in this data?
No.
Okay, because otherwise it will be different, right?
The only way that it would be different is if I needed to bring attitudes into the likelihood to have missing data. Otherwise, I can have missing data on risky behavior and monitoring because they're part of the likelihood. So the model is going to use whichever occasions are complete. So as long as they have, let me say it this way, as long as they have attitudes, it'll be included. But we'll use whichever data we have per outcome per occasion.
Because it's on the between.
Because, it's not because it's on the between, it's because it has to be complete because it's not in the likelihood. So if I wanted to bring attitudes into the likelihood, I would ask it to estimate its mean or variance, and then that would trick the software into thinking it's an outcome. Then we could have missing data on it. But otherwise, we can have partial data over time on either of these outcomes because they're already in the joint likelihood. So nothing would change if we had missing data, other than less power potentially, or the usual missing data issues that you would have. Okay, other questions? So here is the output then from this analysis. Here is the covariance between the residuals at the same occasion. These are the level 1 residual variances for my two outcomes of risky behavior and monitoring. The effects of time invariant attitudes, the 6 pairwise covariances between the intercepts and slopes. That's my fixed quadratic effect. Then here are the two fixed intercepts. Here are the two, fixed slopes. No random quadratic variance. And then here are the time-specific residual variances. Oh, nope, these are random intercept variances, sorry. These are linear slope variances. And then here are the 3 relationships that I want you to pay attention to, that I built into these data. And these are in correlation matrix, so you can interpret them as correlations. So there is a negative relationship between the intercept for risky behavior at age 18 and the intercept for monitoring at age 18. So what would that mean in practice? A negative correlation of 0.46 is what I have here. Of the intercept with the intercept across the two variables. Risky behavior is one, and parental monitoring is the other variable. Any ideas? Go for it. Try it.
I would say the higher the monitoring of parents at age 18, the lower the risky behavior.
So monitoring is a good strategy.
Yeah, I would say so.
Yes.
Or 18
At 18 years
years
old. At 18, exactly. Likewise, there is a negative correlation between the two linear age slopes, which describe the change from age 12 to age 18. So girls who increase more in risky behavior are either increasing less or decreasing in monitoring. So it's the idea of change in monitoring related to change in risky behavior. It's an inverse relationship. So as monitoring increases, risky behavior decreases, or something like that. Correlations among slopes are tricky because you have to think about whether the variance is in the amount of increase, the amount of decrease, or around a middle point where you could potentially have both. And in this case, what we have is increase for risky behavior, but increases or decreases for monitoring. So these two slopes are negatively related as well. Another monitoring is good for you idea. But then the residual relationship is a positive correlation of 0.35. So if I am being monitored more than usual at a given occasion, more than my trajectory says I should be, then my risky behavior is also higher at that occasion. That's what a positive correlation would mean. And you can think of that either way. That I need to be monitored more than usual because I'm behaving worse than usual. Or maybe I'm rebelling, right? Maybe I am behaving worse because I'm acting out because I want you to leave me alone, Mom. Something like that. So I've set these relationships to be an opposite sign to sort of make a point that what is true in terms of between person differences is not necessarily true in terms of within person fluctuation. So these are the three relationships that we want to try and recover. And then there are other associations between the two intercepts and slopes for risky behavior but not for monitoring, and then cross relationships of the intercept for one variable with the slope of the other. So then how do I phrase these things in terms of predictive relationships? We're going to step through and change one thing at a time and see what happens to the results. First, though, we're going to do a single-level SEM version of the exact same model, where this is the picture that goes with it. So conceptually, this is the diagram that would describe the model, where I have my intercepts and slopes for monitoring as my outcome, for risky behavior as my outcome. Everything is correlated with each other. Attitudes is predicting both of each. And then the residual at the same occasion is related across. So what I just described as a multi-level SEM, I could also estimate the same model as a single-level SEM using wide data instead. So here's the long to wide syntax that we've seen a couple of times. The difference in the syntax then is how the latent variables are defined. So I'm using t-scores to define the loadings so that they are person-specific. That's what Levon does not have. So I've got intercept, linear, and quadratic for risky, intercept and linear for monitoring. Here are all the fixed effects in the brackets. Here are all the random effect variances when you list the variable by itself. And then all of the widths. These are the within variable relationships between the intercepts and slopes. Here's the effect of time invariant attitudes. And then here are the cross relationships between the intercepts, between the slopes, and between the two. And then p-width gives me the pairwise residual correlations. And again, I am computing the predicted correlations out of these covariances, and I end up with the same numbers. So there is really no reason to try to do this model one way versus the other in this instance. You could add latent variables for item level measurement models either way. Each of these boxes could be treated as a latent variable potentially if you had a measurement model underneath. Okay, questions so far? No? Okay, moving on. So if I keep the level 1 relationship as a covariance, and I change the level 2 relationship between the intercepts and slopes to be directed paths instead. So I have monitoring on risky and mlin on rlin. That is saying the intercept predicts the intercept and the slope predicts the slope. Everything else is still a covariance. Then the relationships that I get back are going to be between level effects. So I have the between person prediction of one slope from the other, the between person prediction of one intercept from the other, and if I take those unstandardized coefficients and I standardize them using the variances that I just got from the previous model, so just the typical way that you would go from unstandardized to standardized in single level models, then I end up with the same 3 numbers as my new relationships. So it works either way. So then in order to interpret these, you would have to know what a unit means in terms of change for each of these variables, as well as level of each of these variables. Here's the same thing in the SEM version, where I'm switching to direct effects rather than covariances for level 2, and they will be between effects because at level 1, I only have a residual covariance. Same numbers, either way. Now, if I change the level 1 relationship to be a directed path instead, so I'm on page 8 already, then as long as I do so using this direct syntax and not the placeholder syntax, these relationships will, the intercept to intercept path will remain between, but the slope to slope path becomes contextual. I don't know why. It's just what happens to it. Once you adjust for that difference, though, then you can get back to the same relationship between the two that the other model gave us. So this is where it gets to be really tricky to figure out what's between and what's contextual, because it's not always consistent within the model. Some paths are between and some paths are contextual. The SEM version of it works the same way. So if I switch if I have my directed paths at level 2 and the residual paths, I have my pawn to have directed paths instead. Then I have a intercept to intercept and slope to slope relationship. Here's my level 1, and here, yeah, there are the other ones over there. Then if I switch to the placeholder syntax, then the intercept and slope paths become contextual because I've switched the way that I've defined the level 1 model. So this is all chapter 9 in my book, by the way, which is why I'm going through it quickly. But as I have a caveat here, if you switch to Bayesian estimation, everything stays between, which might be a reason enough to try and do it, so it's not as confusing. Here is the same version in SEM, where we end up with within and contextual effects because I'm predicting the relationships directly between the residuals, as we had earlier today in the cross-lag panel models and stuff like that. Now here is the structured residuals thing. This is new. So the picture that goes with this idea is this one. Remember these little intermediate latent variable things that we move the variance over to them? This is what it looks like. So I have new latent variables that I stuck an F in front of the name. So it looks like frisky, but it's actually F risky, is the way that I read that. But we can go with frisky. So these are setting up the structured residuals for risky. What I am doing is saying I have a new latent variable that is perfectly measured by the old observed variable for the residual. I then shut off the old variable's residual variances, and that transfers all of its variance to this new term. So it's literally just renaming what was a residual variance with a new latent variable. But the impact of doing that is that the paths that we end up with are then between effects rather than contextual. That's the rationale for doing the structured residual thing. So I've got a set of residuals for risky behavior, a set of residuals for monitoring. Here they are. And then every relationship subsequently is specified as a function of those new latent variables rather than the original residuals that came from the growth model. So now I have cross-lag effects, where I have monitoring at the previous occasion predicting risky behavior at the subsequent occasion, as well as risky behavior at the previous occasion predicting monitoring at the subsequent occasion. So this picture right here essentially is what I've got going on. And interestingly enough, I have one of them that turns out to be significant. Let me find where that went. Over here. The relationship from risky behavior to monitoring is significant at the lag, but the opposite is not the case. And I can tell you this is not in the simulated data. I didn't put this there, but it showed up anyway. It's a very small relationship if you standardize the parameter, but it's still considered to be significant. So the rationale for doing this structured residual thing is so that all of your level 2 paths become between instead of contextual in some cases. That's why one would go to the trouble to set this up. I then fit a version of the model where the lagged effect is controlling for the contemporaneous effect, and it looks like that actually made the results a little bit stronger. So all of these files, by the way, are in your download folder, each of the models and the output that goes with them, the full thing, so you can look through those later on when we are less tired. And here is some brand new stuff. So courtesy of the latest developments in Mplus, starting in version 8.1, they've added all this new stuff, and it keeps getting more and more. I think they're up to version 8.8 or something. In multi-level modeling syntax, the same idea of having a lagged effect requires a new symbol in the code. At this point, I think they've used every special character on the keyboard. I think they're out. Like every other one is somewhere in the code at some point. But this piece right here is new. There is an option to introduce lagged variables. So these models are only available using Bayesian estimation. So what this is asking for is to take the variable that's on the previous row, essentially, and to bring that into the model. So you don't have to have wide data to be able to fit lagged effects in this. There's also ways that you can tell it to interpolate across unbalanced time so that your lag relationship stays constant, even if you don't have all of the observations that you would need to keep it constant. I forget what it's called, but it's a procedure that is known in other contexts as well. So they borrowed this architecture to be able to do that. But this lagged effect then allows you to access the previous occasion's variables and stick them in the model to predict the current occasion as well. And that's the part that's underlined right here. It's the, I'm going to go with, is that a caret? That's what I would call this thing. It is above the, looking for it, above the 6 on my keyboard. Yeah, I will call it like how you get squared, like caret 2 in certain packages, but it's called a caret, at least to me. I don't know why, because it's not a vegetable. It's a different kind of carrot, I guess. But this then says that the lagged effect of monitoring can predict current risky behavior, and more particularly, it's the residual part only. So this is doing the implicit person mean centering in latent space that we did before to get the lagged effects. So this is one thing that's relatively new that wasn't possible the last time that I gave this example. So this is how you can do lagged effects in multi-level models within multi-level SEM. And in particular, the addition of these lagged effects changes what it's called. They call this dynamic multilevel or SEM when we introduce the idea of this lagged autoregressive type of effect. So if you see those words in the literature, these are the model additions that would trigger that change in terminology. Yes?
This work for like a diary study predicting next day? Is that
It would. And if you don't have the next day, like if it were 2 days apart, then there's an additional piece of syntax you'd have to specify, I think, to make sure that it understands that it's like to keep it constant. Because otherwise it doesn't make sense to have the same relationship if they're different time intervals. And so it essentially tries to interpolate across your data so that it can make it make sense. So it's only in base, exactly. All of these developments are not in maximum likelihood. You have to switch to base to pull this off. So I haven't had a chance to play with these new developments as much, but I did try to compare what I got out of the SEM and what I got out of the MLM. And I have the maximum likelihood solution here with the lagged effects that we got. So this is the concurrent correlation between the residuals. This is monitoring to risky behavior at the next occasion. This one is risky to monitoring at the next occasion. And the results are pretty much the same. Even though we're switching differences in estimation, if they're using non-informative priors, it should converge onto the same answer, which I believe is what they're doing. And one thing that I think is hilarious, by the way, in the Mplus output up to this point, there's been no stars, like stars for p-values for significance. But in the Bayesian output, they literally have a column for stars, even though there's not supposed to be p-values in Bayes land. What? And it's a one-tailed p-value, and I have no idea what it means, to be honest with you. This is two-tailed. But I can tell you that the estimate and the standard error, or their Bayesian equivalence, this is a measure of central tendency. I think it's the median by default, if I remember correctly. And then here's the standard deviation of the posterior, which is the analog to the standard error. These sort of agree roughly onto the same answers. So I don't know what the stars mean. But these were the changes to the model that I thought you could try as an activity if you were so inclined. And I have the solutions, as I said, inside the thing here. So I will tell you as a spoiler alert, this fit a random slope for the concurrent effect of risky behavior. When you try to do it in SEM with maximum likelihood, it won't let you. The model doesn't converge. So that would be a reason to choose this version of the model where you have the multi-level setup as opposed to the single-level SEM setup. Random slopes are much harder in the single-level SEM setup. And that's all I wanted to say about that. So I know that was very quick because I think we've hit our limit. But as I said, we covered some of this in Chapter 9. I will do this example again in my spring class. I did a version of it, I think, in 2018 that doesn't have this piece because it wasn't available then. And I went over it more slowly, I think, in those cases. So those would be other places that you could see this. So when you're fitting these models, big picture is try to pay attention to between versus within. That's the one thing I want you to take with you out of this. And when you're fitting lagged effects, think about, is it the within person effect that's being lagged? Because that's the only thing that makes sense. You can't have last time something predict next time something when you're the same person the whole time. It can only be the within person part that makes sense to have it as a lag. So whatever you're doing to the model, throw those random effects in there to make sure you're at that point. All right, questions? Then we had wanted to be done by 4:30, we said? We met that goal. How's that? Anything else that I can tell you about or point you towards or help with before we bid adieu? Nothing's coming to mind? Fair. Well, if anything comes to mind, by sitting here for 2 days, you have all earned the right to bother me over email. Because it's not a bother. So let me know if you have follow-up questions, if there's anything that I can help with. I know I'm speaking with some of you tomorrow, but for those of you I'm not, the offer still stands as well. Let me know if I can help. That's all I can say. And thank you for hanging in here with me and staying awake and paying attention and all the things, because I know it's not easy. So I appreciate it.
Thank you for making it interesting and also like from a perspective that you understand where it can be hard and difficult sometimes.
It is difficult. Yes.
Teaching is also like, it's not just that you stick with it or something, you also made it very accessible.
Good. Well, that was my goal. So, well, I'm going to hang out for a little bit if folks want to talk to me. Otherwise, I hope you all have safe travels back to where you live. And yeah, let me know if I can ever help.
Thank you so much.
Okay. Yeah, I'll knock it out.